In the video 24 on the foundations of computational economics, we'll look at an approach for optimization, which is through discretization. Well, this method is often also just called grid search. This is quite an elementary technique for finding a maximum or minimum of any function. And the reason that we want to know about it is that it's robust. It actually works with very nasty functions. It's derivative free, and it allows you to find at some significant cost, at least allows you to find a global optimum in case there are multiple local optima in the function. Everything else about it is, not advantageous. It's slow, it's imprecise, it doesn't scale to multivariate problems, but still used quite a lot in economics, actually. And the reason for that is that we truly may have a nasty function to work with, following the economic model. But more importantly, grid search can be used quite efficiently as a first step method in the multi-stage algorithms. So let's see, let's look at it in more details. Well, the algorithm is very simple. Imagine that we want to maximize some function of x. We take a starting value x naught, and then just basically define some region around that x naught, which I called I here. And, it can be defined with some bounds, or maybe the problem is bounded already somehow. Then the point is that we can discretize this region of search, this region of interest, with, say, n points, xi, so that xi's are all in the region of interest. Then compute f at each of these points and return the maximum f as the result for the maximization problem. Of course, this is not going to be the true maximum unless by chance, but it might be close as n goes increases. So that's the whole algorithm. Let's look at the example and implement it. So imagine that we want to maximize this function here, the fourth degree polynomial. We can write first order conditions, and we've seen this in several videos before. Well, nicely, this third degree polynomial can be factored analytically into these three factors, where I just take out the x plus 1. Right from here, you can do that as well, and then apply a quadratic formula. So we can compare to the true solutions whatever the grid search gives us. Let's start coding this here. The standard preamble for the NumPy and the plots. Here's my function, the derivative and the second derivative of the function, just to take a look at the second order conditions, and the critical value, which we just saw calculated analytically, which I put into the list. All right, here's, oh no. Let me run this and run this again. So here's our function. We just created some lean space and plotted the function in red, derivative and second derivative, and the critical points, right? So this gives us all of the complete picture. Here's the function. There's a maximum. There are three critical points here. That's where the second derivative meets 0, and there are two maxima, two local maxima. The second derivative is below 0 in both of these points, and one local minimum. And of course, the global maximum is over here. So let's try to solve this optimization problem by solving first order conditions. And I didn't want to copy the code for Newton method again, and instead let's do this. We've done this already at least once in the past. I'm adding to the path a directory which is here in static include. This is where I put the modules. They should be available in the lectures repository to you as well. This is where all the static files that come with these Jupyter notebooks reside. And then I want to import optim as O. Now, let's look at it again. Optim is here. So this is the file which has a collection of solvers, bisection, Newton, successive approximations, and the Newton in 2 dimensions. And all of this we have written in the previous videos. You can ask for help. This is where the importance of the docstrings becomes very obvious. You know, this module optim has these functions with these input arguments and these descriptions. This is where the file results resides. Okay, so let's just try to build the let's try to use Newton method on this problem. Here we want to start it in different starting points, like so. Okay, and append the list of the x stars. You can see here that I'm calling aw.Newton. So this is going to be a Newton method that comes from the module which is imported as O, just to make it short. Okay, and here we are. As we've seen in the previous video, it is very important where you start Newton. And so from 3 different starting points, we've converged to 3 different solutions. So from this, we know immediately that there are multiple solutions in this first order condition equation. And we don't really know what the maximum is and what the minimum is. Well, we do, and we could check the second order condition in the code as well, of course. And we could also find the global maximum and differentiate it with from the local maximum as well. But that would require some additional code and, you know, some additional logic around the solution method itself. The point is that Newton by itself doesn't deliver us the answer, although it solves the first order conditions really fast and really accurately. But let's try grid search then. So here's the little function. It doesn't even have iterations, so I'm not sure we should include it into the optim file here. I've included it and then marked it out, or commented it out. The arguments are the function itself, the bounds where we want to perform the search, and the number of grid points. What happens is that we create the grid using linspace, very similar to what we do when we want to plot something. Here's a little trick. I want bounds to be a tuple, and to convert tuple into arguments, we just add a star in front of it. So this converts a tuple into arguments list, and a double star converts the dictionary into argument lists, as we've seen before. And the number of grids, that's the number of points. Okay, so linspace produces the grid between the bounds. Then we want to evaluate the function in all of the points of the grid. And then I could have written the for loop to test these functions to find the maximum on them. But I'm just simply using the argmax function from NumPy. And this is the function that returns the index of the maximum element in this array. And then, of course, this grid search returns the element at that index from the grid, which is just grid of I. So let's look at the bounds between -1 and -2 and 2, and we'll do the grid search using the function that we specified, this function f that we specified before. Now, I want to check the accuracy of the solution. So here's the CR is the, I want to look at the index, at the element in the critical values, which is closest to the found solution. How do we do that? We'll take critical values and subtract the solution, the x star. Well, we'll look at the absolute value, of course, the distance between the found solution and the closest critical point. And I want the argmin. So this is very similar to argmax here. Here's the index of the element which attains the minimum. And then I want to take that element with that index from the list of critical points, and that's going to be my closest critical point to the solution found by the grid search. And that's reported then. And we can see here that the grid search returned 1.111, and the closest grid critical point is 1.2. The difference is what, about 1/100th? Oh no, about 10%. So the difference of about 0.1. Can we change this? Can we change the error? Well, one thing we can do is we can increase the number of grid points. And as you can see, now it's about 200th. And if I increase the number of grid points even more, then we go to about 100th and even more. So now we're getting something like 10,000, right? So the X star moves pretty close to the critical point. And by the way, it's very obvious that the grid point method picks out the global maximum pretty accurately. We're always looking at the correct critical point here, indicating the robustness of the grid search, right? It is the global optimizer in that respect. But how fast does this accuracy increase if we increase the number of grid points? This we can check. Let's look at this little code. Data is going to be a dictionary where n is the number of grid points, and I'm just using the list comprehension here. This is the powers of 2 right up to 20. So these are going to be different number of grid points. The error is initialized, allocated with the same shape. And then we'll go through the list of this length of the grid points and perform the grid search with the corresponding number of grid points. And then, do exactly same operation and calculate the error, save it into the ith in the correct position in the data. Just calculate the difference between the solution by the grid point by the grid search method and the closest critical value, and then just plot them. It'll take some time to compute, of course, and here's what we see. Now I've made the vertical line the y scale, the y-axis on log scale, and so as we increase the number of grid points, we can see that the error decreases quite fast first, okay, but then it sort of slows down. And think of a Newton method, right? It takes, what, about 7-10 iterations to get down to 10 to the minus 6, which is not a very high accuracy at all. That's what we have here, 10 to the minus 6. With the grid search, you have to have an enormous number of points on the grid to reach the same frequency, to the same accuracy. And of course, I'm using regular grids here, which basically means that we have to fill out the whole interval between -2 and 2 between the bounds with points situated really, really close to each other to improve the accuracy of the solution that we find. Because we don't really know where the solution is, that might be necessary. So this is a fair comparison. At least to some extent, just plain grid search method to the other solvers. It is very inefficient. It is very inefficient. But so what's a better, what's a more appropriate example for grid search then? Well, look at this function. What if we had this function to work with? And this is a monster. If we code it up and look at the plot, let me go to this view. Here's the plot of this function. It's pretty crazy, right? So it has cases and it has different function forms in each of the cases. And on the plot here, the vertical segments here, they don't exist. It's just the way that I've made the plot, that these points are connected, but in fact each time we have a discontinuity here. So think of this vertical segments as not existing at all. This is very hard function to optimize. And why is that? Well, it has kinks and non-differentiable points. And that's trouble for Newton method, right? Because Newton has to have a derivative that is possibly to calculate at each iteration. Now, the discontinuities themselves may lead to the fact when there is no root at all, or there could be no maximum. So thinking of 1 over x, if I want to find the root of the hyperbolic function, of course I can't, because there's discontinuity where the root would be. Now, if I came up with some numerical smoothing of this function and sort of smoothed this discontinuity, then probably this is where the root would be, but because of the discontinuity, it just doesn't exist. Similarly, if we want to calculate the maximum of this function, well, the maximum doesn't exist neither, because it grows to plus infinity over here. Same thing goes for minimum. So functions which are discontinuous are really nasty function indeed. There can be, or in the example that we just looked at, there are multiple local optima as well. There are flat regions as well. And flat region is bad because the derivative is 0, and it's both that Newton can be trying to divide by 0, or that the criterion doesn't change. So the numerical procedures do tend to get stuck in the flat regions as well. So in this example, discretization might be the only option. And indeed, nasty functions like the one that we've just seen, we could encounter them in economics. It's both from the estimation procedure that we may have kinks in the objectives. The economic models may have this really terrible functions. And then we don't have any option but to work with them. Or it could be that the function is just really costly to compute, or really costly to study from the theoretical standpoint. Or maybe that's the whole point we're using the numerical methods, as the function is the subject of the study. We want to understand how it behaves. And when we don't know much about the function, it's hard to choose a numerical method to work with it efficiently. And finally, another case that I can think of is the robustness checks. So sometimes you have a numerical model and it has some parameters which we either decided or we can't really sort of plot some object of interest as a function of those parameters. And they can be categorical variables, for example, where you have to try one by one, sort of like a grid search. Or they could even be assumptions, right? If we want to make a robustness check with respect to assumptions, then we may want to do, a grid search over the space of the assumptions. In any case, coming back to the function that we just looked at, here's how the grid search would deal with that nastiness. So using the same grid search to solve it, let's first visualize what we're doing. So I've drawn the function here, and then over here we're visualizing the grid, right? So let the grid be as in the grid search subfunction, a lin space with bounds and number of grid points fixed. And then we just put a bunch of markers, vertical line markers in color black, on the points where the grid points happen to land. And here we are. So if we call it between -2 and 2 with 10 grid points, here are the grid points. You can see they're, in small black lines. And to put a star on the X star, after the problem is solved with grid search, we also put a marker star, asterisk, where the solution is found, right over here. Okay, so as you can see, kind of visually, the optimum is in a different peak, and even grid search cannot find it because the placement of these grid points are sort of by chance. So it's a very rough idea of what the function is. What do? Well, we increase the number of grid points, and you can see with 20 grid points now we get them spaced more densely, and we pick out the second peak over here, which is higher than the previous one. So we improved the result here. Now, can we get to the actual maximum of the function? And yes, we can. So here with 30 grid points, we actually are very close to the true maximum of this function. And by the way, this maximum is defined correctly because if we go to the formula here, it's a cube which is inclusive of the upper bound, right? So this point here is actually included. All right. Well, can we do better and move it, a little bit closer if we increase the number of grid points yet again? Oh no! What happened is, with more grid points, suddenly, the other local maximum got a point closer to the optimum there, and we're back to this level, unfortunately. So you can see that even grid search is having hard trouble with some of this nastiness of this function, and because this peak here, the one that contains the true optimum, is so narrow, we have to be lucky to place the grid point exactly where it needs to go. And just cranking up the number of grid points to a really large number allow us to robustly get to the optimal point there. Okay, so that's the performance of grid search. Oh, it's worth saying then, but any other method with this nasty function would just not work at all. So grid search is providing us with some degree of reliability of the result here, whereas any other method would just fail. So what about the poly algorithms? Like I said, grid search is a really good choice for the first stage of a poly algorithm. The idea is that it can robustly find some promising region. And if you keep the number of points low, then it's also quite fast. And it doesn't need to be accurate to be in the first stage of the poly algorithm. So it's not a bad idea to run a grid search of the problem that we don't know much about. Say we don't have theoretical properties for the objective function and we just want to get into a better starting value. And then on the second stage, run a more accurate algorithm, for example, Newton method, which would be initialized at the solution produced by a rough grid search. And this technique is often referred to as multi-starts, where Newton method is started many times, for example, at the regular grid. The hope, of course, is that Newton method is started in the domain of attraction after running this initial grid search. Now, even without the Newton method, it's also possible to formulate what's called an adaptive grid search, where you put a grid search in a loop, and every time it finds a rough approximate of the maximal point, then you can run this next stage grid search close around that point, trying to put more points in the promising region rather than in any region. And that can be generalized to multiple dimension in the method which is called pattern search. Okay, and on some further learning, it turns out that that grid search is actually used quite a lot in machine learning. The way that I've mentioned already, which is to test or to find better values for some special parameters of the algorithms, so hyperparameters as they're referred to. And here's some information on that. Okay, that's it for this video. See you in the next one.